So where does the law come from? Well, we learn in school that the law comes from the legislative branch of the government. When Congress passes a bill, it becomes law. But this is only part of the story. Most cases, most court cases, when they're heard in front of a judge, are a straightforward application of existing law. But some cases are more complicated than that. Some cases, the judge has to interpret the law. When this happens, the judge writes an opinion, a text document saying, in this case, we decide the following for these reasons. But these opinions are more than just opinions. These opinions, these written documents, are actually law. In the United States and other common law countries, we follow the principle of stare decisis. What stare decisis means is courts are bound by their decisions. So when the Supreme Court issues a ruling, that becomes the law of the land. That is actually new law, what that judge wrote. It also means that you have to rely on precedent. So when you're examining a case, you have to look back to what previous courts have decided. So in this talk, I'm going to talk about open data, networks, specifically the networks of cases and how they cite each other. We're going to talk about identifying important cases in that network. And maybe at the end we'll talk about community detection. So if these opinions are so important, if they're law, where can you find them? Well, if you go to a law library at UNC, for example, or maybe a large law firm, you'll see these giant rooms filled with these large, boring, dusty-looking books. They're called law reporters. When courts issue opinions, they're written up in law reporters. There's millions of them. Now, if you're thinking to yourself, this sounds a little, old-fashioned, I can't apply a regular expression to a physical book, well, you're right. Now, there are digital sources of legal data, such as LexisNexis or Westlaw, but none of them are free. Large law firms, pay for their services, and maybe one opinion is 10 cents or something like that. But what if you want a lot of opinions? What if you're a public defender or something like that? What if you're a networks researcher who's a grad student? 10 cents times a couple million documents is more than my stipend. It doesn't have to be this way. Legal data is not owned by anyone. There's historical reasons why it is this way. But what about making legal data free, accessible to the public? Enter the Free Law Project. The Free Law Project is a nonprofit that aims at providing free public access to legal data. They have a website called Court Listener, where you can find a fairly large amount of data. So they have 3 million legal opinions and counting. These opinions include the text data, who was the judge who wrote it, when did the opinion happen, where was it, etc., etc. They have a database of judges, almost every judge. And they have data about the judges such as who appointed the judge, what are the judge's political opinions, have they donated to any of the major political parties. They also have about 800,000 minutes of oral arguments. These are currently being transcribed by Google's speech-to-text API. So Google is actually training its speech recognition algorithm on Court Listener's dataset. And also Court Listener's dataset is becoming indexed so people like you and me can examine it. Now there's other sources of free legal data such as Ravel and Google Scholar. And they're all great. They all have their pluses and minuses. But we'll focus on Court Listener today. So Court Listener makes bulk download of your data easy. One click to download 3 million court opinions. So that's about a 30 gigabyte compressed file. I'll confess, I don't know how big it is uncompressed because I tried to open it on a shared Dropbox and may have crashed on my collaborators' computers. But it's, fairly sizable amount of data. Importantly for us, it includes the citations. So court opinions, like academic articles, cite each other. Court Listener also offers a case recommendation system called Zeitgeist. So, when you go on Netflix, Netflix says, you might be interested in watching Narcos, which you all should watch. It's kind of amazing. So you do a keyword search. They do some basic NLP, word2vec, etc., and then come up with a list of cases, and they return the top 10 or top 20. And so they have some notion of case quality. And right now, that notion of case quality is based on the citations. We'll come back to this. So what is a network? Well, the great thing about being a networks researcher is everyone already knows what a network is. Everyone's on Facebook. So basically, a network is a set of nodes, so people in a social network, and a set of edges, a set of connections. Ian and Abby are friends. There can be different kinds of networks. Networks can have metadata, so nodes can have values, such as a name, a physical location. Edges can be directed, so if you're looking at academic papers, one paper will cite another paper. That's a directed edge. You might consider that undirected, but it's naturally directed. Other edges can also be undirected, so Abby and Ian are friends. That's an undirected relationship. Edges can also have weights. Now, there's a lot of networks that people are interested in. Social networks are some of the most famous, Facebook and LinkedIn. Neuroscience, my other research is in neuroscience. So on the right, we have an image of someone's brain. And what that is, more specifically, is a diffusion tensor image that is registered the hundreds of thousands of long, wispy white matter fiber tracks connecting all of the neurons in your brain. On the left, a network representation I'm trying to learn something about. So the network we're interested in today is the network of law case citations. So for example, so in our network, the nodes are legal cases, Brown versus Board. These cases cite each other. Remember, by stare decisis, you have to rely on precedent as much as you possibly can. So our edges are citations. They're naturally directed. Sometimes we'll consider them to be directed. Sometimes we'll consider them to be undirected. If you ever look at a network data set, this is an important data choice that you probably want to consider both. We have about 3 million nodes in our networks, about approximately 3 million cases on a court listener, and about 30 million citations. So this is a fairly sizable network. One important feature of our network is there's no cycles. It's called a DAG, directed acyclic graph. So basically what that means is the edges all go roughly in the same direction. You can't cite a case that has not happened yet. Case in 2000 can cite a case in 1900. Case in 1900 could not cite a case in 2000. Today we're actually going to focus on a further subnetwork, the SCOTUS subnetwork. SCOTUS, the Supreme Court of the United States. That has about 30,000 cases and 250,000 citations. A citation is between two cases from the Supreme Court. So for our analysis, we did it in Python with Jupyter Notebooks. And there's a lot of open source graphs, networks package. By the way, graphs and networks, they're interchangeable. Nodes, vertices, cases, interchangeable. So we use two. We use NetworkX and iGraph. They're both wonderful packages, both open source. NetworkX is written in Python and is really great documentation. There's example code. You actually read the documentation. It's useful. You can find an example of what you want to do, copy, paste, change a few things, and you're good to go. iGraph, on the other hand, is written in C under the hood. So it's a lot faster for large networks. And it's wrapped in Python and R, so you can use it if you don't know C. I don't know C. Unfortunately, there's poor documentation for Python. And this is not trivial, because what it means is it takes a long time to get started. There's good documentation in R, just not in Python. So this is something we're working on changing. But that matters. So when you're designing software packages, think about the user. The problem is there really isn't example code in Python for some reason. It's like a example code desert. So what questions are we going to be interested in? Well, I think the first question everyone's going to think of is, what is the most cited case in legal history? Or basically what you're saying is, can we identify important cases from our network? What does important even mean? Can we understand how legal precedent evolves? And can we help Court Listener and other websites build a better case recommendation system? So I'm going to pass it off to Michael to tell you a little bit about notions of important cases.
So to determine which SCOTUS cases are important, we'll be looking at three centrality measures mainly: in degree, closest centrality, and PageRank. So visualizing large networks is pretty hard. The first thing you want to do when you get your data is you want to look at it. You want to visualize it. But we took a default layout in iGraph to visualize our data using a physics-based heuristics approach. And what we got is a big ball of nodes and edges, and it just looks like a jumble of mess. It tries its best using its algorithm to place the nodes and edges as as beautifully as possible. And we tried other heuristics layouts, and they didn't really do any better. We kind of got the same results. So let's talk about in-degree and closest centrality. In-degree of a court case is basically the number of citations that court case gets. And this is a pretty intuitive centrality measure that most people should do because it's the first thing that'll come to your mind, right? It's pretty easy, and you're just seeing if the most important court case is the most cited court case. And closest centrality is based on the notion of the distance between two nodes. So the shortest path, so the distance between two nodes is essentially the shortest path between two nodes. So the distance from Sam to Abby would be 2. And in a directed graph, you can only travel in the direction of the edge. So you're only traveling in the direction of where the arrow is pointing at. So Sam can walk to Dan, but Dan can't walk to Sam. In summary, closest centrality measures how close a vertex is to all other nodes in the graph. And closest centrality of V is defined as 1 over the summation of the shortest paths from V to all other nodes. So in summary, if the distance of the shortest paths is small, then the closest centrality is large. But this comes with a downside. We have to compute all pairs of shortest paths. And this actually is cubic in the algorithm time in respect to the number of nodes. So we talked about using 2 different packages to analyze our data, NetworkX and iGraph. It took 7 hours to do it in NetworkX, but it actually only took 5 minutes with iGraph because it's C under the hood. It's a lot faster.
I should say the developer time was also reversed. iGraph, it took 5 minutes for me to write. NetworkX, sorry, iGraph, it took 7 hours for me to write. NetworkX, it took, you get the point.
NetworkX, great documentation. iGraph, we made a Git issue saying they need better documentation. So let's look at this toy plot example. What is the most important node? According to degree centrality, B would be the most important case. It has 5 degrees. It has the most degree. So it's getting cited the most. But according to closest centrality, case A is the most important case because it's the closest to all other nodes in the graph. And it's an interesting observation that A is between 2 separate clusters of nodes at the left and at the right. Exactly. So let's measure SCOTUS by in degree. So we have this plot. It's a visualization. And this network looks a lot different from the one we saw before. It's not a big ball of nodes and edges, and it might actually be telling us something. So this is actually our SCOTUS network plotted where the node's x-coordinates are the court case's dates, and the node's y-coordinates are the court case's in degree. And we can already tell that one of the court cases has a pretty high in degree. It's getting cited a lot. So let's look at that. This is the US versus Detroit Timber and Lumber Company case. It has 600 citations, and it's about twice as many citations as the second most cited case. So this is a pretty it's a pretty big case. You might think so initially, but we found out that it's actually not an important case, and I'll explain to you why. So law reporters often write, sometimes write, cliff notes or summaries about these court cases, and lawyers often cite these cliff notes and summaries as opinions, and by stare decisis, opinions are law. What this means is that the lawyers are essentially using the cliff notes in the same way that they would use opinions issued by judges, but cliff notes obviously aren't law. So Supreme Court recently ruled against this practice. So after this Detroit case, the court cases will have a little syllabus written by the law reporters, and it'll have a little footnote saying, the law reporters are saying, please don't use this footnote as an opinion or as law. See the Detroit case. And this kind of explains why it has such a high end degree, because court listener citation parser accidentally picked up this footnote as a citation. So that's a data quality issue that we actually fixed, and it's an example of a data quality issue. So let's measure SCOTUS by closest centrality now. And before we looked at in degree for a directed graph, right? You can't really look at the number of citations a court case gets in an undirected graph. But for closest centrality, since it's we're only dealing with shortest paths, we can look at a directed version of SCOTUS and an undirected version of SCOTUS. So closest centrality on the directed graph. When you look at this, it doesn't really tell us much because closest centrality is a function of time, right? So it's saying that the most important court cases are the latest court cases. We're not really interested in that. However, when we plotted closest centrality on the undirected graph, it looks a lot more meaningful. So we consulted our law student, James Woodall, and we listed the top 10 court cases by the highest closest centrality values, and we found out that most of them were procedural cases. So what are procedural cases? Well, procedural law is about how the courts operate. So it explains how our legal system works. And this means that two different court cases from different areas of law can cite a procedural law because it explains how our legal system works. So let's look at an example. This is Erie Railroad versus Tompkins, and it explains about how the body of law operates under federal courts. And this is a pretty important case because this allowed federal courts to make law about states in different jurisdictions, or about, so if two different state courts are handling some case, now federal courts can make a decision about those two different states. So that explains how closest centrality is between two separate clusters of nodes now, right? Because it's basically close to all other nodes because a bunch of court cases from one area of law is going to cite this procedural law, and a bunch of court cases from another cluster of law is going to cite this procedural law. And I'll hand this off to Iain to talk for PageRank.
Thanks, Michael. So PageRank is one of the most famous network algorithms. It's actually what is underlying Google search. PageRank basically says you're important if you're cited a lot and you're cited by other important cases. Page in PageRank is actually a play on the words web page and Larry Page. Larry Page, the founder of Google. Should also mention court listener, one of the main people working on it, his name is Mike Listener. So see a theme there. So PageRank was originally motivated for networks of web pages. So in this network, the nodes are websites and edges are directed hyperlinks between websites. So I post an article to my Facebook, and Facebook then links to the New York Times or whatever. One thing to note is there can be loops. So my Facebook might have a link to my LinkedIn, which then might link to my blog, which might then link back to Facebook. So remember, in the citation network, that can't happen. That's important. So what's the intuition behind PageRank? It's actually pretty simple. Imagine randomly surfing the web in the following way. Go from website to website to website by clicking links. When you're on a website, that website has a link to a few other websites. Randomly pick one of those links. Do that for a really long time. Very occasionally, pick a website totally at random. Doesn't have to be connected to your current website. Now, how long did you spend on Facebook? What proportion of the time did you spend on a given website? That's the value of its PageRank. So for example, the sum of PageRanks in a network sums to 1. PageRank defines a random walk, and it's a Markov chain in a finite state space, so we can write down a transition matrix and use solve for the principal eigenvector to compute the stationary distribution. The upshot of that is it's quick to compute PageRank. It's just a couple matrix operations. So it was, just I think it was a couple seconds on my computer, both on iGraph and NetworkX for 30,000 nodes. So let's rank the Supreme Court cases by PageRank and see what happens. Well, here are the top 10, and you'll notice that PageRank tended to pick older cases. So most of these cases are from the 1800s. The cases that PageRank picked were not necessarily themselves landmark cases, but they preceded landmark cases. So for example, the slaughterhouse cases. They were the first cases to chip away at the 14th Amendment. So the 14th Amendment is the right to due process. When it was originally written, there was a very strict interpretation of it. So the slaughterhouse cases ever so slightly expanded that interpretation. Not of note, but slightly. Started a trend. The slaughterhouse case by itself was not important, but it started this trend. And this trend led to the Civil Rights Act, and the legalization of gay marriage. So the slaughterhouse case was not a landmark case, but it led to landmark cases. So that's interesting that PageRank picked those. Here's a plot of PageRank values versus time, and you can see PageRank tends to favor older cases. It's not extreme. I'm hesitant to use the word bias because I don't really know what an unbiased ranking would mean, but you could say this is biased to favor older cases. So here's the Erie Railroad case, for example, that was marked important by closest centrality. It was ranked 94th. So PageRank said, yeah, it's important. It's important. Remember, there are 30,000 nodes, but didn't rank it in top 10. So PageRank and closest centrality, they're getting at different things. Here's the Detroit lumber case, which, remember, received a huge number of citations, but was not, actually that important. Well, PageRank ranked it 65th, so it didn't say it's irrelevant, but it didn't rank it in the top 10. If you remember that in-degree plot, that was a huge outlier. It was twice as many citations as other cases. So in some sense, PageRank is robust. So PageRank realized, yeah, you've got a lot of citations, but you weren't cited by important people. So, you're not so important. So that's an interesting feature of PageRank, that you always want your algorithms to be robust. So why does PageRank favor older cases? There's actually a pretty nice explanation of that. And the problem, or the reason, is we have a DAG, a directed acyclic graph. So remember, citations all go backwards in time. There can't be loops. If you remember how the random walk works, it follows the direction of edges. So maybe we started a case in 2015, and then we jump down to 2010, and then we jump down to 2000. And sure, it'll sometimes occasionally jump all the way back up to 2015, but in general, PageRank wants to walk backwards in time. So PageRank is going to spend most of its time in older cases. The proportion of the time that you spend on a case is PageRank. Therefore, PageRank in a directed acyclic graph will prefer the older cases. So that's important to know if you ever want to use PageRank in a network, particularly a directed acyclic graph. I'm sure this is known, but I couldn't really find this anywhere online. So there's other measures of vertex centrality, such as betweenness centrality, which basically says you're important if in some sense you tend to be between other cases. Betweenness centrality is similar to closest centrality. And it also picked out similar cases. It tended to favor procedural cases. So remember, procedural cases are sort of the ones linking the many areas of law together. A couple more algorithms, the hubs and authorities algorithm and eigenvector centrality. These are both similar to PageRank. And they basically say you're important if you've got a lot of citations and you've been cited by important people. Hubs and authorities and eigenvector centrality tended to favor substantive cases, so cases about a particular area of law. They actually both favored First Amendment cases. I think 8 of 10 and 10 of 10, the top 10 cases from these two were First Amendment cases. So that's our legal collaborators found that pretty interesting. Other legal researchers have found that authority scores actually match well with sort of legal expert opinion. So that's always something you want out of your rankings. Well, it's something you may want, that it matches with what the experts think. So this is a plot of authority scores versus time, and you'll notice that the authority also did not pick the Detroit case as one of its top 10. You know, it ranked it highly, but again, was somewhat robust to the number of citations. So the Detroit case was not cited by important cases. Authorities did not think that it was important. So that's a great feature. Authority scores tended to favor cases in the middle of the 1900s. So that's good. I mean, that's sort of intuitively what you might think where the most important cases would be. So what have we learned? Well, every dog has its day. There's not a best measure of vertex centrality. There are different measures that get at different things. Depending on your context, you might want to pick one or the other. So to Court Listener, we're recommending some improvements to their recommendation system. And this also applies to other case recommendation systems from other legal websites. So using other notions of vertex importance. In-degree is a good place to start, but there's other measures that you might consider. Probably authority scores is the one I would go with. Actually, a number of websites use PageRank, which, as we've seen, is sort of biased to favor older cases. It might be worth implementing multiple recommendation systems or giving the user an option to say, I want a procedural case or I want a substantive case. You sort of might be thinking to yourselves, well, where's time in all of this? If a case in 1920 received a lot of citations, well, maybe that case is not so important in 2016. Well, it doesn't show up anywhere. And none of the sort of standard measures of vertex importance that you'll read about in a network textbook explicitly get at time decay. Actually, almost all of them will sort of favor older cases just because the longer you've been around, the more time you've had to be cited. So that's actually something we're actively thinking about. How do we sort of take time into account? The answer is probably going to be some kind of statistical modeling. And as a stats PhD, that makes me very happy. So now I'll talk a little bit about community detection. So community detection is about identifying clusters of nodes in a network. It's clustering in a network. So roughly, a community is a group of nodes that are very densely connected to each other and sparsely connected to the rest of the graph. That's a heuristic statement, and there's 400 different ways to make that precise, but roughly that's what it is. So one of my collaborators, James Wilson, applied community detection to his Facebook. And I will say he wrote down ahead of time what he was expecting to find, as a good statistician would. And he discovered 7 communities. I think he had said he would find 6. But they corresponded pretty well to his Facebook friends, to his college friends, his grad school friends, etc. So, here's an example that, of course, I selected where community detection worked wonderfully. I should note that James also invented that community detection algorithm. Community detection is unsupervised learning. So unsupervised learning is great. You can do wonderful things with it. You can find unexpected things in your data. But when you apply a clustering algorithm, you get clusters. Does clusters mean anything? Maybe. Maybe not. There's a million different community detection algorithms, all with different motivations. So you have your classic optimization based. Here's a reasonable objective function to let's try to maximize it. Oh well, it's NP hard, so let's apply some heuristics at it. Or maybe let's write down a statistical model and apply maximum likelihood estimation. Or for Bayesians, and I'm sure there's some Duke people here, you might do posterior inference. I'll confess I'm becoming a Bayesian. So what's going to happen if we apply community detection to our legal network? I've done this, but it's preliminary results, so I won't share anything with you. But you might expect to find court jurisdictions. So there's about 400 jurisdictions and 400 or 500 jurisdictions. So the North Carolina Supreme Court, the North Carolina State of Appeals, the South Carolina, blah, 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 blah. You might expect that cases within communities will cluster together. So that's what you would expect. But what about finding unexpected communities? That's sort of what we would hope to find. So for example, there's no good reason why one jurisdiction should favor another. So there isn't a good reason that North Carolina's Supreme Court should favor the South Carolina Supreme Court. They're geographically close to each other, but legally that doesn't mean anything. But what if they do? That's interesting to know. That's something community detection might be able to pick up. Also, community detection might be able to pick up sort of small areas of the law. So, you can imagine maybe there's 50 cases that are all kind of about the same thing, and maybe they, tend to cite each other. Maybe community detection can pick that up. Can we just turn that on its head and use that as a statistical model to understand how this network grows? That's sort of the direction we're going right now. So to summarize, open data is important. Open data is important for everything, but open data is particularly important for the law because legal opinions are actual law. If your access is restricted to legal opinions, then in some sense your access is actually restricted to the law. We believe in an open judiciary in this country, so that's not a great thing. If we don't have open legal data, then we can't do macro analysis of the network. Sure, I can pick up a legal case and read it, but I can't analyze 3 million legal cases without access to open legal data. We learned about a couple different notions of vertex importance, and I imagine maybe some of you have network data sets or will at some point in your life have a network data set. It's worth considering them all. It's also worth considering your network to be directed or undirected. What is the basic unit of your analysis? This is something we all face. How do I look at my data? Well, in networks that's important, and there's data object choices. Directed, undirected. Do I consider my edges to be weighted, etc. And PageRank tends to favor older nodes in a graph, in a DAG. So that's important if you're applying it to a DAG. So just to summarize where we're going right now, you haven't heard me talk about much statistical modeling. I haven't fit any parameters, which makes me feel anxious as a statistician. So that's what we're doing now. We're writing down some models. There's some standard models for how a network grows, and they're all good. But we actually have a network data set. We have an evolving network data set, so we can actually fit some models to this. And that's sort of what we're most interested in. We're also interested in we haven't talked about the text data at all. We have 3 million text documents that broke my friend's computer. Well, can we combine that with the citation information? If we apply some kind of document clustering like topic modeling and find all these topics, well, does that correspond to the network that we'll find from the clusters that we would find from a network-based community detection algorithm? What about combining those? Thank you.
Hi. Because it favored the older cases, have you looked at trying to predict what recent cases will in the future be? What was the term? Authority cases?
Authoritative cases.
Authoritative cases. I noticed on the graph there was one that looked very recent that was, it wasn't very high up because it was so recent, but it was significantly higher than the ones from the similar time frame. And it looked like, 20 years from now, that will be in authoritative cases. But have you looked at trying to predict which ones? You gave a couple of examples of types of cases that stood out as authoritative. Were there any other things like that? Yeah,
well, so in terms of sort of trying to predict, that's sort of that's doing some statistical modeling. So if we fit some model to our network, we might have a couple motivations. One might be to sort of understand what's driving the growth of this network. Another might be to try to actually predict what's going to be cited. So that's certainly something we're looking at. And so not yet, but that's we're in the process of doing that. Oops.
Do you have any idea what the recent case that was slightly higher than the other ones was?
I'm not sure which case you're referring to, but why don't we talk about it after?
Sure. Okay.
Now, got 2 mics. Look at that.
I know it's a fringe case, but what about cases where there's an appeal after a few years? That would change the assumption of directed cyclic graphs, right? Because at time T1 there was a case and it was cited by many cases, but then T1 was repealed. So can there, if the new T2 case cites back the cases and there is some new evidence or new procedure set up, then the directed assumption will be changed, right? And how would it change the rankings if possible?
So the directed assumption would not change in that case, because when a case comes out, it would, when a case is, when you write an opinion, you wrote down the citations there, so you can't like go back in time and change that to a future date. You can't really cite something that hasn't happened yet. But you did bring up an interesting issue. Cases can be appealed, they can be revoked, et cetera, et cetera. In some cases, court listener will sort of squash those cases together. In some cases, they'll consider them as separate. That's something we haven't taken into account now, but that's something we're actively thinking about. How do we? In some cases, it makes sense to sort of treat them as the same thing, and in other cases, you should treat them as different objects. But yeah, we're looking into that.
Let's start back here. This mic.
I wondered, how does the network-based prediction work when something has dramatically changed in the law? For example, in 1 year, the government decides to remove the death penalty, and then how does the citation network reflect the change? Like time series problem.
Yeah, that's so my advisor has been sending me a lot of papers on time point detection. So that's my advisor's a probabilist. So we're sort of thinking about probability models for change point detection. Sorry, in a network. There's some work about that I will be familiarizing myself with. But yeah, that's actually a really interesting question. I mentioned a network researcher named James Fowler, and they sort of looked at just the raw out degree of cases over time. So how many cases do I cite? And what they found is before the early 1900s, maybe you cite one or two, but in the early 1900s to maybe 1930, there's a giant jump in that graph, the out degree. And so what that says is people started taking stare decisis seriously in the early 1900s. So that's something that legal scholars had sort of, always thought, roughly in the early 1900s, people started seriously considering stare decisis. I need to rely on precedent for my case to back it up. And they provided some empirical evidence. So I don't have the chart, but it's, as you can imagine, it's just, ooh, boom, goes way up. That's just very clear evidence. That's a change point in the network. Yeah, it's certainly an interesting question. That's probably a PhD thesis right there. Maybe it will be my PhD thesis. I don't know.
And had a quick question. Would it be worth attaching this data to sociological data to see how divorced court decisions are from what's going on in society, or whether they anticipate what's going to happen in society or they react to?
Yeah, that sounds like an interesting but hard thing to do. We have all of these these legal opinions. That's a lot of text data, and I imagine that you could try to tie that in. Yeah, it's an interesting thing to do. This is a really interesting data set, and it's there's a million different ways that you could attack it that are all like genuine research questions for legal scholars or for statisticians, etc. So yeah, I encourage you to think about how you might do that.
Hi. I guess. Is this still working? Okay. So I'm just curious if you looked at, so at least for the Supreme Court, it's considered important by a lot of people that they're independent of their politics, sort of. So I'm just curious if you examined anything about how the political affiliation of the judges affects how they ruled on cases or anything like that.
Yeah, so that's we're not looking at that, but there's a number of people who have and actually currently are looking at that. So the judge database was compiled by I think a grad student at Princeton, and he's sort of actually looking at sort of exactly that. Looking at how politics affects the way judges rule. And when I mentioned the judge database, they put a lot of effort into sort of putting the judges' political affiliations in there. So that data, the data set is there or growing to sort of actually get at those questions.
So it is 12:10. I want to go ahead and wrap us up. Maybe one more round of applause for Michael and Iain.